Imagine standing high in the Andes, on a knife-edge ridge. The mountain wind screams across the precipices. If you drop a stone over these cliffs, you'll wait several seconds before hearing it strike, if you hear it at all over the constant Andean gales. A single misstep here means plummeting thousands of feet to your death. Yet, 500 years ago, entire work crews built architectural masterpieces on these vertical cliff faces. They had no iron tools, no wheels, no written blueprints, and no modern safety equipment. Just stone tools, grass ropes, and human ingenuity. Modern construction crews with cranes, steel cables, and safety harnesses still struggle to build on terrain like this. So how did the Incas construct massive stone cities on impossible cliff faces while maintaining remarkably low casualty rates? The key appears to have been a revolutionary principle: when gravity tries to kill you, make gravity work for you instead. This approach guided every aspect of Inca cliff construction. To understand this safety architecture, we must begin with the most fundamental challenge: how did they even reach these deadly sites safely? Before a single stone was cut, Inca engineers had to solve the fundamental challenge of access. The solution lay in their incredible transportation network, the Capac Nan, the Great Inca Trail. This trail crossed deep valleys using suspension bridges that supported llama caravans and military units hundreds of feet above roaring rivers. The Quesoacaca Bridge in Peru demonstrates this perfectly. It is the last surviving Inca rope bridge, rebuilt annually using traditional techniques. This process reveals that local communities, working simultaneously from both sides of the canyon, coordinated movements with ancestral precision. These bridges required engineering that accounted for wind loads that could send a person tumbling into the abyss, seasonal weather changes that turned rope fibers brittle, and varying weights from military columns or laden llama trains. Their fiber technology was remarkably sophisticated. Inca rope makers created specialized load-bearing cables with different fiber compositions for specific applications. Some ropes were stiff for structural support, while others were flexible for safety lines. Crucially, each rope was likely tested under controlled loads before use in cliff environments where failure meant worker deaths. Imagine the tension as workers tested each strand, knowing their lives depended on that woven grass holding firm over empty space. Once access was established, the Incas deployed their most significant safety breakthrough, their terracing system, which essentially converted deadly vertical drops into stable horizontal work platforms. Modern mountaineers and construction workers still use this exact principle when working on cliff faces, creating stable platforms rather than depending entirely on ropes over open space. The physics were brilliant, but the scale of excavation was immense. Workers had to carve backwards into solid mountainsides, hauling countless tons of rock debris along narrow paths. At Machu Picchu, this system transformed an unbuildable steep mountainside into stable construction platforms. Crucially, each terrace level provided secure footing for construction crews while serving as permanent structural support for the buildings above. Workers could build walls while standing on solid, level surfaces, feeling granite bedrock beneath their feet, instead of depending on precarious rope systems. Studies at the site suggest these terraces solved multiple life-threatening challenges simultaneously. They provided stable platforms that wouldn't collapse under worker weight, they managed water drainage to prevent catastrophic landslides, and they created agricultural space for food production. Construction likely began during dry seasons when soil conditions were stable enough for safe excavation. Any mountaineer will tell you that water-saturated ground on cliff faces can shift from stable to deadly in hours, turning secure footing into landslides that kill everyone in the path. Rain, snow runoff, and groundwater could quickly transform stable construction sites into muddy death traps. The Incas addressed this through hydraulic engineering that rivals modern cliff stabilization techniques. At Machu Picchu, they installed sophisticated drainage, channeling water through the city via a carefully calculated series of fountains. This created the musical sound of controlled water flow, a stark contrast to the destructive roar of unmanaged runoff. Calculations by water engineer Kenneth Wright show that the fountain system could move more than 300 liters of water per minute. After 500 years, these channels still function exactly as designed. The channel bringing water to Machu Picchu is 750 meters long and was designed to descend 10 meters for every 100 meters traveled, ensuring that gravity could maintain a consistent flow. The terraces incorporated these drainage systems to safely channel water away, preventing the saturated soil conditions that caused landslides, a deadly threat that could turn stable ground into a killing zone within hours. Here is where Inca engineering reached its most sophisticated level. What stunned researchers was the discovery that the Incas would work stone directly on construction sites rather than hauling massive blocks up cliff faces. This decision alone likely prevented numerous accidents where one wrong step while dragging a multi-ton stone meant falling thousands of feet. The famous precision of Inca stonework wasn't just aesthetic, it was crucial for safety. Imagine workers balancing on narrow ledges, chiseling joints so perfect that 5 centuries later you still can't slip a knife blade between the stones. When blocks fit so perfectly that mortar wasn't necessary, construction crews didn't need repeated dangerous adjustments while balancing multi-ton stones over cliff edges. This zero-error fit eliminated the need for precarious trial-and-error positioning. Research at sites like Ollantaytambo shows evidence that the Incas used specialized local quarrying methods that prioritized precision over speed. Workers would study each stone's internal structure, identifying where to place bronze wedges and apply pressure to achieve desired shapes without multiple dangerous repositioning attempts on unstable cliffside surfaces. Furthermore, the Incas developed specialized tools designed specifically for cliff construction safety. Bronze crowbars and wedges were designed with extended handles that provided leverage while keeping workers away from cliff edges. Stone hammers incorporated balance features that may have prevented slips during repetitive striking motions on precarious surfaces. Building safely on precipices requires flawless coordination in environments where communication errors kill instantly. All cliffside work appears to have been organized around the Ilu kinship system, extended family groups that had worked together for generations. They could instinctively coordinate movements where split-second timing meant life or death. Systematic training protocols likely prioritized safety. Young workers may have spent years learning stone cutting and rope work techniques in safe valley locations before approaching cliff construction sites, developing the stable balance essential for extreme altitude work. The ceremonial calendar that coordinated construction activities also functioned as a weather-based safety protocol. Work schedules were synchronized with seasonal patterns to avoid construction during high winds that could knock workers from ledges, heavy rains that turned stone slippery, or temperature extremes. The entire system worked because each phase built upon the previous one. Stable terraces provided platforms for precision stone cutting. Integrated drainage prevented water damage. Systematic training ensured workers could execute complex maneuvers safely. And quality-controlled materials meant equipment wouldn't fail at critical moments. The Incas achieved something remarkable. They developed systematic methodologies that converted deadly challenges into manageable procedures through the careful integration of engineering, organization, and sophisticated safety systems. They proved that true engineering genius isn't about having the best technology, it's about understanding the problem so deeply that your solution becomes unbreakable.